What's up? My name is Alex, and my AP research project this year was about solar energy. $236,719.79. That's a lot of money. Think about what could cost so much. We'll come back to this. First, I'll talk a bit about how I got here. I remember 4 years back, I came to school for the first time as a freshman, and I passed by the solar array in front of our school. I thought it was really interesting and wanted to learn more. So 4 years later, I finally got the chance to fulfill this interest. At first, I was clueless about what specifically to research, but then I saw the duck curve, a phenomenon that is the greatest problem affecting solar energy today. The top curve here shows the amount of energy a fossil fuel power plant needs to produce over a day to meet demand. As solar has grown over time, the amount of energy traditional fossil fuel power plants need to generate to match demand decreases, so the curve is lowered. But when the sun sets, there's no more electricity being generated from the sun. So suddenly, these plants have to ramp up production to match the continued need for electricity at night, which is hard to do. And this makes a duck-looking shape appear. But what if independent locations like schools can produce their own electricity and store it as envisioned in the future? This problem could be easily minimized. The goal of this study was to model solar panel electricity generation based on a single solar panel at the high school, extrapolate on a larger scale, and find the return on investment. This study seeks to answer if the implementation of solar panels at high school A would be an affordable alternative to non-renewable sources. To begin, why renewables in solar? There are three main reasons. First, energy security. Fossil fuels are being depleted at a faster rate than being found, meaning we will need new sources soon. Second, energy independence. Many fossil fuels come from the Middle East, which has historically had lots of conflict, putting fuel sources in jeopardy. And third, climate change and global warming. Burning fossil fuels releases more CO2 into the air, which is a greenhouse gas and makes the Earth warmer. This extra warming has many side effects, such as wild animals changing their behavior and migrational patterns. Scientists believe that infectious animal diseases like COVID-19 are going to become more prevalent due to the increased human and wild interactions brought about from these changes. Some background on the case study. High School A is one of the largest schools in the 14th largest school district in the U.S., and it serves more than 3,500 students on a given day, meaning it has a large carbon footprint. In 2015, in partnership with the Walton-EMC and Green Power EMC's Sun Power for Schools program, a 1.3 kilowatt solar panel was installed, so implementation already exists on a small scale. As a commercial property located in a dense residential area, High School A represents one area of potential growth to aid in achieving energy security and independence, while reducing the effects of greenhouse gas emissions and climate change in the local area. At first, I wasn't exactly sure what I was going to study, so I just looked up a lot of journals. The first type of literature to look at was about city planning and case studies, and these papers revealed a common barrier to solar installation was government bureaucracy. Some schools across the country have attempted to install solar, but there has been stiff resistance from the government. In the city of Atlanta, Johnson explains the lack of coordination between the city and the Atlanta Public Schools Board made implementation tough. For Atlanta, the city felt money could have been better used to invest in solar in places like community recreation centers. In other cases, governments may have pre-existing policies that do not have solar and or other renewables playing a large role in energy production. In Minnesota, one factor that stifled the completion of the project was government bureaucracy and legislation limitations on solar, as explained by Grimley and Giavarini. The second type of literature dealt with the physical solar panels themselves and the economics behind them. These papers showed a common barrier to installation was that of subsidies. One type of subsidy is the producer subsidy. This type is intended to promote increased competition between domestic and international solar panel manufacturers, which drives down costs, as Girardin explains. Consumer subsidies, on the other hand, are for customers themselves. In the United States, one of the most common is the Federal Investment Tax Credit, the ITC, which provides a tax credit of 30% for solar investment costs. However, there's one caveat. This credit goes towards federal income taxes, so a nonprofit organization like a school will not qualify because they don't pay federal tax to begin with. An alternative to this is to allow third-party companies that pay federal tax to house solar systems off-site, as Oldfield explains with what happened at the Colorado School of Mines. Overall, there have not been enough subsidies to really spur widespread adoption. The third type of literature was about news reports on High School A and statistics on solar panels. They gave background to the case study and revealed a final barrier to solar adoption: technology. According to the Solar Energy Industries Association, the energy in 1 hour of noontime summer sun falling on the U.S. is equivalent to the annual electricity demand. Still, the average efficiency of solar panels, the percentage of sunlight that can be converted into electrical current, only hovers at max around 20%. Even though solar potential around the world is immense, humans have failed to capitalize on its potential. Fact sheets from the U.S. Department of Energy show that innovation is occurring, and companies are now able to use materials that cost less in their final product, but there are still efficiency and reliability limitations. A common analogy can be drawn to Moore's Law, which describes how computer chips doubled in speed and processing power, while simultaneously decreasing in cost and size. That's how we're able to get such small computers like smartphones today. Until we reach a similar point with solar panels, widespread adoption will not occur. Together, these factors combined with pre-existing statistics on High School A will be factored into return on investment and will be used in this study. Let's talk a bit about how this experiment worked. In order to calculate return on investment, an experimental and evaluative research design analyzing quantitative data was used. This design was chosen since it would test for current trends from existing data and also allow future models to be developed. The first step of experimentation involved studying the electricity production of the pre-existing 1.3 kilowatt solar array. Originally, I wanted to calculate the solar panel production capacity, also known as the DC capacity, using the formula below. However, this couldn't be done for the school with the pre-existing solar panel because this panel was a residential one for experimental purposes. Commercial ones that would be installed are more dense and can produce more electricity. I still decided to analyze the data since it could reveal trends in solar over time, and because not many people know about this data at my school. I used a computer program that auto-tracks it called Locus NOC, seen up here, and I downloaded the data in a CSV file. Here are the results. Over the entire lifetime of the system, this one solar array produced on average over 3.02 kilowatt hours of electricity a day. To put this into perspective, this can only power about a computer and a printer, so definitely not a ton of electricity. One thing to note is that average electricity generation is decreasing. This could be due to reasons such as different amounts of rain or sunlight from year to year, but rain data has shown that even in extremely rainy years like 2018, it doesn't seem to affect solar production much. Temperatures have also remained fairly constant over the testing period. More likely, this trend is due to a decrease in the effectiveness of a solar panel. Solar panels are like lithium-ion batteries in your phone. They can't hold as much charge over time, or in this case, create charge. This decrease in maintenance costs will also need to be factored into return on investment. The dataset was fairly consistent overall, showing solar actually does work at High School A. Step 2. Analyze how many solar panels can actually fit on the roof to determine total capacity. Solar panels can technically be installed anywhere. However, at High School A, it is limited to the roof since, as mentioned before, the school is located in a dense residential area without open fields. As such, only roof areas were considered in this study. First, each part of the school was sectioned off as seen here. Rectangles were used because solar panels are rectangles, so that would make the most mathematical sense. The areas were measured using the Google Maps measurement tool since it is open source, easily accessible, and backed up by various GPS and street measurement systems. During this process, I realized there could be a way to improve the layout of solar panels. Solar panels can be either laid horizontally or vertically, so it doesn't matter since the sun is still going to hit it at the same angle. Take a look at this example. Let's say we have a roof that measures 17 feet by 10 feet, and standard solar panel dimensions seen here on the left. We can choose to place these solar panels in two orientations, 1 and 2, seen here on the right, through calculations seen in the chart and diagram. On orientation 1, we have a 3x3 arrangement for a total of 9. Now in orientation 2, let's reverse this arrangement, and due to the area and shape of the roof, It's only possible to fit one row of 5 to avoid solar panels hanging off the roof. Same area, different orientations, and a much different number of solar panels that can be installed. On a large scale, this could be the difference between many solar panels. To efficiently compare these calculations, I created a Java program that takes in the parameters. Here's a demonstration. This code ran on Replit, which is a web-based compiler system that can automatically run code. This program asks for a length of the roof, so we will say 17, and also a width, which we will say 10. And just like we calculated before, it will give us an output of 9 maximum solar panels that we can fit. Well, that video was kind of sketchy, so I'll make sure to link a better one in the description. So, as we found on the last slide, this program shows that the area calculated is actually true to a hand calculation. So for roof areas that could fit thousands of solar panels, this definitely was a big shortcut when calculating. When you add all these calculations, you get around 16,818 solar panels. High School A is kind of shaped like a rectangle, so if you treat it as one big rectangle and measure, you will get around 17,000. So this measurement system with the program worked out pretty well. In the end though, I had to take a 30% deduction because there needs to be buffer zones for maintenance workers to move, as suggested by an industry expert named Mr. Walker from the local EMC. Some irregularly shaped areas on the roof were marked out with a slash line, as these areas were deemed too small or did not have good solar potential because they were wedged in between two other sections, and it created a shade. I needed a baseline to see how much High School A actually uses and what we currently pay for regular grid electricity. This is necessary to see how much the solar panels would need to generate to cover the current electricity usage and how the current cost compares to solar, which as mentioned before, has an expensive initial cost. To do this, I used a 12-month energy audit from the local EMC, the school's energy provider. Here was the report for 2019, the last full year of testing, and it was a pretty representative year. High School A used about 2.85 million kilowatt hours of electricity. Now remember that number from earlier? It turns out that's how much the school paid for electricity last year, more than $200,000 just for electricity. I also got some rates and pricing from the EMC. Grid electricity currently costs around 8 cents per kilowatt hour, so this will be the baseline comparison cost. As mentioned, our school roof can fit a maximum of around 11,773 panels with deductions, so that's around a 1 megawatt capacity, since 1 megawatt is about 10,000 solar panels. This amount can cover around 10% of total current usage. The final step involved calculating a return on investment using data from prior steps. I used a pretty standard return on investment formula of savings minus costs. Any percent return on investment greater than or equal to 0 means you will save money with solar. Any return less than 0 is uneconomical. You're losing money, although you are being good for the environment. Some things can't be measured in dollars. Using all the factors we calculated before, it's possible to calculate return on investment. Solar panels currently cost at bulk around $2.75 per watt to install. There's an estimated maintenance cost of $10,000 a year for 25 years, the estimated lifetime of the system. These two factors are the costs. As mentioned before, it may also be a possibility to get a federal tax credit, although that credit is decreasing rapidly. It's down to 26% this year and will continue to decline. Combined with the 10% of total energy costs saved from no longer needing to use grid electricity, these two represent the savings with a solar array. Altogether, the costs come down to paying an extra $140 a month for 25 years for a solar array that can only cover around 10% of energy needs. This makes it pretty clear that solar is not feasible for High School A at this time. There are many reasons for why solar currently is not viable. First, High School A uses a significant amount of electricity annually, and its location doesn't provide enough space for solar panels to generate this large amount of electricity. Second, current electricity rates are relatively inexpensive. Pre-existing infrastructure and subsidies make non-renewable sources much cheaper than solar. Solar pricing is simply not competitive. Third, solar is not a mature technology yet, as mentioned before. The low efficiency and reliability requires a lot of panels to produce a little electricity. Other factors include external variables such as government subsidies and maintenance costs. The ITC has dropped, and annual maintenance costs total more than half of the annual energy savings. This study shows that schools with lower energy use, high land availability, and sufficient financial resources are the best candidates for solar today. In the future, perhaps lower costs and better technology will expand the pool of feasible applicants. During this research, there were a few experimental errors, mainly in the measurement of the roof. It would be challenging to find the original blueprint or physically scale the roof to take measurements, so the Google Maps measuring tool was used. While this measuring tool is accurate to fractions of a foot, satellite error or human error when using the tool could have existed. Another factor could have been the presence of vents or air conditioning units on the roof that may limit installation in certain areas. To correct for this was factored into the 30% deduction for buffer zones. Another general drawback is the positioning of solar panels. In the northern hemisphere, and specifically at High School A's location, solar panels should face south at 34 degrees due to the tilt of the Earth. In this study, the south direction and tilt were not taken into account. This is because accounting for the direction and tilt would not be the most efficient use of roof space. By right triangle trigonometry, as shown here on the right, the solar panels in this study were oriented approximately 30 degrees west to south. Since the maximum return on investment produced a negative value, the standard measurement demonstrated in the middle image was not used. Implications. This methodology could also be applied to other schools as well, provided things like an energy use audit and regional price quote are provided. In this school district, there is at least another school that has a similar floor plan, as seen here on the left. A main takeaway from this research project was also the development of a more accurate solar calculator. From research, it became evident that current solar calculators do not necessarily provide an accurate return on investment. One calculator took in insanely unrealistic parameters and still gave a positive return on investment, seen here in the center. The methodology of this research suggests a new, more accurate solar calculator can be created, one that also includes a roof optimization method, which current solar panel calculators do not have. The biggest implication for High School A is the topic of conservation. A key component of why solar is not viable is the extreme energy use prevalent at High School A. The most notable culprit was during the summer months when school was not in session and there was still significant energy use. If electricity use was reduced dramatically through simple steps such as turning off lights or computers when not in use, solar would be much more viable. Finally, for future improvements of this experiment. For one, I could obtain a blueprint or personally go onto the roof of High School A, if they allow, to measure the lengths, widths, and areas of each section of the roof. A computer section or program, such as GIS, which stands for Geographic Information System, to model solar panels would also yield more accurate results. One area of future study could investigate live weather patterns and solar panel absorption. While a weather station was present with a solar array, the data was not very usable. It is known that solar panels work best with direct sunlight, so cloud cover, rainfall, and other factors such as pollution and smoke could affect absorption. Studying battery storage could be also an option if there is excess electricity production at certain times in the day. This has been identified as just one solution to help solve the duck curve phenomenon. However, this would add an additional cost to installation, which we already know is a lot. Solar panels on the sides of schools could also be studied. Futuristic schools such as the Copenhagen International School in Denmark employ solar panels in areas such as the exterior walls, even though these areas are more subject to shading. Through this project, I learned there are small steps that can be taken immediately. Students and administrators can work to conserve energy during non-school hours. These small steps would make solar much more reasonable under today's circumstances. Personally, I wrote a grant to a local energy company for a solar panel in our school's literary garden. If successful, this grant would be used to power lights in the garden and help teach others about the potential of solar. Here are my references.